just to give a silly example to start with, imagine that you have an artist friend who decides to color all the integers. That is his thing today. All integers must receive a color. Now, you don't know what colors he's going to assign to all these integers, but you know two things. You know that the first integer is going to receive the color blue. Okay, so 1 is going to be blue for sure. That's the first thing you know. Another thing you know, that an integer if that is adjacent to a blue integer is also blue. So if I have something that it's next to something that's blue, then this something has to be blue. So that's from that, you get to conclude that every integer is blue. What is a predicate? So let me ask you a few questions before I give the principle of mathematical induction. I mean, this silly example of coloring integers with blue or whatever, that I think is clear. What is a predicate? That's question one. Another question is, well, what is a proposition to begin with? What's a proposition? Maybe I should ask that first. And then I'll ask, what's the propositional function?
Proposition is something which is like a statement that's true or false.
Exactly. So a proposition is a declarative statement in English that is either true or false. Okay, that's either true or false. What is a predicate?
Isn't it the same thing? It's either true or false, I believe.
Okay. So so a predicate.
It's not a statement that we're going to prove.
Okay, so the proposition is a statement that is either true or false. A predicate is so a proposition has a subject and a predicate. Okay, so subject is what this proposition is about. For example, the sky is blue. The sky here is the subject. An integer is colored blue. The integer 7 has the color blue. The integer 7 is colored blue. The 7 is the subject. The predicate is something that says something about the subject. So being blue is what's being said about the integer 7. Being blue is what's being said about the sky. That's the predicate. Predicate says something about the subject. We'll denote the predicate by P. So you can think of it as a property of an integer as well. So the property of an integer, the property of being blue, the state of being blue is the property of an integer. So P of 2, or let's think of another property of 2. 2 is an even number. Let's say 2 is odd. Okay, that proposition can be either true or false. So 2 is odd. So what is the predicate here? The predicate?
Being odd.
Being odd is the predicate. This is predicate. Okay, but clearly 2 is the subject. We're talking about 2. So the predicate about 2 is the property that 2 is odd. Now that can be that is a proposition. 2 is odd. Now that is either true or false. Okay, this one happens to be false, but it could be some other proposition that's true about 2. What is a propositional function? Okay.
The outcome of the value of the function, either true or false.
Now that's a Boolean. But so the proposition takes those values. So the proposition itself can have one and only one of those two possibilities, true or false. That's true of a proposition. A propositional function. You're correct so the propositional function, just to be loose about it, it is a set of propositions indexed by n. N is a variable here. For each fixed n, I have a concrete proposition. So concrete proposition for each fixed n. Fixed n. I get to vary n. So it is a function in n. It is true that the value of this is either true or false. But depending on what n is, the proposition is either true or false. So for example, if n, so I get to vary n, if the p is the property of being odd, if I say something like n is odd, this statement now depends on n. And it's true or false depending what n is. If n is 3, then this is a true statement. If n is 4, this is a false statement, right? So it changes with the value of n. This is what we mean. So now, we're not going to be testing people with about this terminology, but I will be using this terminology as we go along. So I'd like people to be aware of this. And I'll be asking also a couple of questions from logic as I formulate the principle of mathematical induction, right? So if you don't remember, that's fine, but we want to clarify these before we move on. Okay, so that's that. Okay, so now let me ask you a couple of, so here's a quick summary. So P will stand for some property, like the property of the sky being blue, or of an integer being colored blue, of an integer being a prime, and so on and so forth. Generic notation here, P. P of something. It's a property of dot. This dot is the subject that the predicate is saying something about. If you substitute n for dot, then you'll get a propositional function, and this says that the property P holds for this integer n that I get to substitute there. I get to vary n. Okay, that is all good. Now, I'd like to formulate the principle of mathematical induction that you've already suggested what it was, but let's just have it written down on one page. What is it that I'm after? What is the principle? You want to, the goal is to establish a property about all integers n, starting from some integer, like, I don't know, 7 and upward, or 1 and upward, or 0 and upward. So the goal is to show that that property P holds for every integer, and this is important that these are integers and not reals or complex numbers, for every integer n. Let's say starting at 0. I could have started at 1 or 5 or anything else. Let's start at 1. Fine. Could be 0, so that, just to be clear. So here's the two things that you've suggested are as follows. If we show P of 0, or since we have 1, let's start at 1. P of 1 is true. And if we show that P of k implies P of k plus 1 for any integer k, then we can conclude that P of n is true for any n. Okay, so now let's parse all of this. And yes, some people may be obvious, but there's something to talk about here. It's true for every n. That's the principle itself. It says, I agree, something that's very obvious, but why do we need it as a principle? So here's what it says. From the base case, I've proven that P1 is true. Then I've proven the implication that P1 implies P2. What is an implication? Okay, this is going to be a side, so let's make it a different color. So just what is an implication?
I think sorry, just like loosely, like if this then that. So like if the like just an example, if the sun is out, then I'll go outside.
Okay, yeah, it's a good example. If it's Monday, then you have a discrete math class. That's an implication. If you're drunk, your cognitive abilities are impaired. That's an implication, and so on. Exactly that. So it is a sentence. It is a proposition. Oh, remind me, what's a proposition? So P and Q are propositions. P implies Q is also a proposition. What's a proposition again?
A true false
Yeah, it's a statement. It's a statement. This entire sentence, if you're drunk, then your cognitive abilities are impaired. This entire sentence is itself either true or false. The question is, when is it true? So let P be, let's say you're drunk, and let Q be your cognitive abilities are impaired. Okay, so what is P implied is Q? how many values? So P implies Q is a sentence itself. It can either be true or false, right? P implies Q. When is it true? When is it false? So we really want to, yeah.
If P is Q and then, I'm sorry, if P is true and then Q is false, PQ or P implies Q is false.
Okay,
It's
I
just
agree
one
with
of
you.
them.
Yeah, that's true. How about, so P implies Q is a sentence. It's again, it's a proposition that can either be true or false. Okay. Now you have four possible states of the world. So for the values of P and Q can be, these are the only possibilities that you have for P and Q, right? Okay. There's nothing else that can happen because each P and Q is a proposition itself. Each one can take independently of the other the value of either true or false. Now, depending on those values of P and Q, P implies Q itself as a sentence is true or false. You've identified one case when P implies Q is false. How about in other cases?
I think the rest of the cases should all be true.
The rest of the cases are all true. That's exactly right. So the only time P implies Q is false is when P is true and Q is false. That makes sense? Okay, so that's, I think everyone's on the same page with this one. Here's what we're proving. Back to mathematical induction. This piece, by the way, is called the inductive step. So the first case is called the basis case, or basis step, or basis case, any way you'd like to call it. And this one is called the inductive step. Inductive step. It's going to be the second piece here. Okay. What we're saying is P1 is true. We proved that in the base case. Then we have proven that P1 implies P2. So P2 must be true. Is true. Then we proved that P2 implies P3. Then we conclude that so P3 must be true. Is true. And so on. Forever. We have an infinite number of implications here. What will be proved when K is any integer. So we're proving this P2 implies P3. We're proving P3 implies P4, and so on. So we're proving all of these propositions. So note on the side, if you'd like, that we're proving an infinite number of propositions in a finite amount of time. So this is kind of a curious fact in itself. So we'll do that all the time. Okay. So we're concluding that P4 is true. It's true. In fact, if K is an arbitrary integer, and if I've proven that PK implies PK plus 1, okay, I'm concluding that so P of K plus 1 is true, and so on. So that's the conclusion. This is just very, very obvious. You can see it from the truth table, right? So if P is true, okay, for me to conclude that the implication is true, I must show that Q is also true. This is what we'll be dealing with, and I'll repeat this several times here. Where after proving the fact that the implication itself is true, the fact that the implication is true lets us conclude that all of these P2, P3, P4, PK plus 1, all of those guys are true. And all of those guys are true. If that's the case, then we get to conclude that no matter what n is, this proposition about n is true for every n whatsoever. Okay, so this is all very much an abstract level discussion here. We need to dive into concrete examples, and we'll be applying this principle. So keep this principle in mind, right? So every inductive proof will follow this same principle. And there's a very specific template that we'll use in every inductive proof. Every inductive proof you write out on the quizzes, on the tests, you'll follow the same template all the time. So after you've done like 10 of them, this should be pretty straightforward to do, right? So let's just do them. So, okay, so I should probably tell you that often when the principle of mathematical induction is presented, people like to use all sorts of metaphorical scenarios to explain the principle of induction. One of the most popular ones is the use of the dominoes. You have a row of dominoes lined up. P of 1 corresponds to knocking over the first domino, and P of 7 implies P of 8. corresponds to, if you knocked over the 7th domino, then the 8th one will be, the one next to it will be knocked over. So if this is true for any k, not just 7, but any k whatsoever, if P of k implies pk plus 1, then you will have knocked over all the dominoes. If you knock over the first one, and you know that knocking over any domino knocks over the next one over, then all the dominoes will be knocked over. That's the principle of mathematical induction. Okay, so let's just get started with the proofs of by mathematical induction and see how many examples can we do today. Here's our first example. I want to prove that the sum of the first consecutive n integers is equal to that. Okay, and we want to strictly apply this principle of mathematical induction. We'll see if proving something by mathematical induction provides any insight whatsoever into why this is true. First, let me show you why this is true. Let's forgetting about induction for a second. Do people have any proofs of this in mind, why this is true? Or do people Google this stuff all the time when you need to sum them up? So you're summing up these integers. Let's say 99. Let's say 100. The first 100 integers. Okay. Okay. Several ways of doing this, obviously. What's way number 1? Go and take a calculator and punch in 1 plus 2 plus 3. Do it 100 times. We'll give you the correct answer. Write a program, some for loop from I equals 1 to 100. Increment I, keep the sum running total. You'll have an answer, and so on. Here's a much nicer way. Notice that 1 plus 100 is 101. Notice that 2 plus 98 is 101. Notice that
2 plus 99 or 2 plus 98?
Oh, yeah, sorry. 2 plus 98 is not what we need. 2 plus 99 is what we need. And that is, I think, 101. As is 3 plus 98, 101. Okay. As is 4 plus 97, and so on. You get the idea. I'm not going to write them down, all of them. Okay. What's the last one here that I need to write down? 49 plus 52. 50 plus, is that 101? 51, is that 101? How many entries do I have?
N over 2?
Yes, exactly. 50 entries, which is n over 2. And that was my question, and you answered it exactly. Okay, 50 times 1, 101. Okay, so that's n over 2. So, okay, that's the answer if you plug it into the calculator. And that is exactly 100, which is n. N is 100. 100 times 101 over 2. That's exactly what I was asking. Okay, so it is true. So this is actually a much nicer proof than the one that we're about to give. But we'll give an inductive proof of this just for practice. And maybe I'll ask later, I mean, what is the advantage of having an inductive proof when you have a much nicer one? And I think once before I've attempted to give a geometric proof of why n why this sum was the same thing. Okay, it's like half of the area of the rectangle, but let's leave that aside. There are gazillions of proofs, gazillions ways of justifying this. But again, we'll give an inductive proof. So here's the outline of the steps. Now let's just review. We've articulated the principle of mathematical induction already, but let's do it one more time. What's my P of n? The first thing you do is not the base case. So some people, all of you probably have seen mathematical induction, or maybe you haven't, but most of you have. You will say that the first thing you do when you write down the proof by mathematical induction is to check the base case. In this class, no, that's not the first case. That's not the first step at all. The first step is to write down the proposition itself, the predicate. What is it that you're proving? The hypothesis itself that you are going to show is true. That will be the first step always. If you miss this, it's just wrong. Okay, so checking the base case is the second thing to do. The first is to write down the predicate. What is P of n? And in the first examples, our predicate will be just very straightforward. You will think that this is just a redundant step. Why should I be writing this down? But if you come across something slightly more sophisticated, you'll see that choosing the correct predicate will make the difference between proving something, the ability to prove something by mathematical induction, and inability to do so. So it makes a huge difference. So we'll get in the habit of writing down the predicate, even though in the first few examples, writing down the predicate will be a very straightforward step. What's the predicate here in this example? What am I trying to prove?
That 1 plus 2 plus 3 plus, whatever plus n is equal to n times n plus 1 over 2.
Yeah, that's exactly the predicate. It's exactly what the problem is asking us to prove. This is the predicate. I want to show that this is true. This predicate is true for every n. Could have started at 0. Well, I'll ask you later, what would it even mean to start this at 0? This is an empty set. You should start this at 1. So that's fine. Okay. So that's the first thing, that we write down the predicate. Let me actually copy this, because I may be pasting this when we write up the proof. Then, once we have the predicate written down, we want to show that this predicate is true for every n. We check the base case. What is the base case here? First of all, what is the predicate P1, the concrete predicate? For n, yeah, we talked, okay, so it's a propositional function. I plug in n, you'll get a different predicate for each n. What is P of 1? This is scratch work. What is P of 1?
Is that just when there's one number in this?
Yeah, so let's just say what the predicate is. Yes, you're correct, but let's say it.
1.
No,
That's or just 1. Okay.
Okay, so that's exactly what I'm asking. And okay, so let's try it again. So what is the predicate? P of 1. This is a concrete proposition. So P of 1 is a concrete proposition.
So would it be P of 1 equals 1 times 1 plus 1
Yes.
over 2?
P of 1 is this concrete version of P of n, right? So P of 1 is this entire 1 equals 1 times 1 plus 1 over 2. Does that make sense?
Oh, I see. You wanted me to add the whole thing. I thought you just wanted me to
No, I wanted
the thing.
No. I want to say it in words. So we're not doing any calculations. We're just articulating the steps, right? So the P of 1 is a sentence. It's a declarative sentence in English, or in a natural language, that evaluates to either true or false. This 1 either equals that which is on the right-hand side, or it doesn't. In this case, it happens to equal that, just algebraically. 1 is equal to 1 times 1 plus 1 over 2. So it is equal. So P of 1 happens to be a true proposition. Can I ask you, this is not going to be part of the proof, but can I ask you what is P of 2? Just to make sure that we'll get this practice.
2 equals 2 plus 1 over 2. Or
Okay.
2 times 2 plus 1 over 2.
Okay, let's try it one more time. Close.
1 plus 2
Yes.
is equal to 2 times 2 plus 1 over 2.
Yeah. So this is a statement about the integer 2. In our introductory example, we're coloring integers by 2, and you said it was silly, and some people ran away. Here, that's another property of the integer 2. What property is it of the integer 2? That every integer beginning at 1 and ending up to me, 2 says, will be equal to 2 times 2 plus 1 over 2. That's the property of 2, which happens to be true. Does that make sense? So let me put it in quotation marks then. Are we all on the same page? Let's just quickly say what P3 is and move on. I know that this is now obvious, but let's just say it, just for the sake of clarity. What is P of 3? It's a proposition. It's either true or false. Like 2 is odd. What is P of 3? What am I saying about the integer 3? It is some property of the integer 3 that I am discussing. In general, in this question, we're discussing some property of the integer n, where n is any integer. So so help me out so I can move on.
So 1 plus 2 plus 3 equals 3 times 3 plus 1 over 2.
That's exactly right. That's P of 3. Now we have to prove this, not just P of 2, for P of 2, for 2, for 3, but we want to prove this for any n, that Pn is true, that this holds for any n. That's what we need to prove. So let's just go ahead and prove it. Okay, so here's the first thing one says when you write down the proof by induction. You say the proof is by induction. Proof is by induction. Okay, that's just simply to alert the reader that what's coming is going to be the proof by induction. Now, given that if the question on the quiz is asking you to prove something by induction, you don't have to write down this sentence. Okay, so nobody's taking off points because of this. But the other steps you must follow to the T. So the proof is by induction. You're just telling the reader that what's coming is not a proof by contradiction or by anything else. It's a proof by induction. There's a variety of kinds of proof. So what's the first thing that I do in the proof by induction again? So hint is that it's not the base case. The first thing that I do is I let.
Write out the predicate.
Sorry, one more time.
You write out the predicate.
You write out exactly. You write out what it is that I'm trying to let Pn be this predicate for each n. We want to prove. So the goal is to show that this predicate is true for every n. Pn is true for every n. Okay. What's the next thing, please?
Then we show the base case is true.
Exactly. Base case. And the base case we actually already checked, but let's write it down one more time. P1 is true because as we just showed, 1 equals 1 times 1 plus 1 over 2. So we're done with the base case. Usually the base case is very trivial to check. It will take you half a second to see it and like half a minute to write it down on the quiz. Okay, most of the work will be involved in proving the inductive step. Okay, so what's the inductive step? Here I will nitpick. So please be prepared when you answer for me to nitpick, which is a good thing, which is what we're doing. So okay, so let's be happy, even if your answer is, let's say, even if I say it's incorrect, right? The inductive step. So what's the inductive step? So what am I doing here?
We make an assumption that the preposition is true at some value k.
Okay, so that's okay. So let me start the nitpick. That's not it, right? Although you will say that in this step, so you're correct. But let's just say in the inductive step. So here's the nitpicking part. We're proving that the implication is true. Okay, let me go back to the principle so you keep that principle on the side always. So what we need to show here is that the implication is true. All this discussion about logic and all of this stuff. The purpose of this was this. When I'm proving, what I want to do is prove that the implication is true. To prove that the implication is true, the only case that I'm concerned in proving that the implication is true is that this is the row that holds. I want to ensure that this doesn't hold. This row here doesn't hold, that the implication is not false. I cannot have the implication being false. Therefore, I cannot have the situation where P of k, this stands for P of k, this one, this P, and this stands for my P of k plus 1. This is a stand-in, but there's these P and Qs. I cannot have P of k be true and P of k plus 1 being false. This I cannot have. This is like no-go row. Cannot have in induction. Cannot have in induction. And those lines, the last two lines, I don't even care about, because if P of k is false, the implication is true anyway. And all I care to prove is that the implication is true. So all I really have to check is that, assuming that pk is true, I want to show that pk plus 1 is true as well. And now let me say that your first suggestion was correct. Okay, so I just wanted to nitpick that the principle itself says that I want to prove that the implication itself is true. That's what allows me to conclude that all of these guys are true. Okay, that will ultimately lead me to conclude that P holds for every n. So P of n is true for every n. Okay, so back to the question. in the inductive step, so let's be a little more concrete now. So to show, again, I'm always showing the implication. To show that P of k implies P of k plus 1, assume P of k is true. And show that P of k plus 1 must also be true. And conclude and show and prove, let's say use show, that P of k plus 1 must also then be true. There's no other way. That's what I'm proving. Must also be true. Okay, so here comes this is the part that you need to pay special attention to. So what is pk plus 1? So let me do a little Simpsons cloud. Here's the Simpsons cloud. What is P of k plus 1? Which I need to show is true. What is pk plus 1?
On this specific example?
Yeah, this is what we're proving here.
So yeah, I know, but like we can say instead of k, n, right?
Yes, instead of n, k plus 1. No, it's not instead of kn, but instead of n, k plus 1. So here's what I'm asking. Just as I asked before, what is P1? Right? So what was P1? Just let's repeat it. I've asked this like a few minutes ago. What was P1? The equality is true.
Yeah.
Okay, what is pk plus 1?
pk plus 1 equals k plus 1 times k plus 1 plus k plus 2 over 2.
That is correct, but I'm going to nitpick. I'm going to say that, okay, so I know that you have a correct thing in mind, but you said pk plus 1 equals that. That's not what it is. But you meant to say, I know, yeah, but you were correct. Here's what here's what you said, you meant to say. You meant to say that 1 plus 2 plus k plus 1 is equal to k plus 1 times k plus 2 over 2. And this is what you said, right? This is what you meant to say. Am I correct?
Yes, pretty close.
No, I thought that was exactly what you meant to
It
say.
was k plus 1 times k plus 1 plus.
Yeah, but it's
2.
k plus 2, right?
Oh, yeah. Yep, sorry.
That's correct.
That's it.
Yeah, actually, I like the way you said it better. So let me just to be clear so that people see it. K plus 1 over 2. That's actually clearer. Is that what you said, right?
Correct.
Right, okay, so that's exactly what we want to show, that is true. So I want to show, so you start with pk plus 1 in inductive proofs, that 1 plus 2 plus k plus 1 equals something. Now I'm going to have to justify this. This is in my Simpsons cloud. This is what we need to prove. This is what we're after. So this is like, we don't know that this is true. We want to show this. We get to assume the inductive hypothesis. What is the inductive? Now let me ask another question. So this will be our clean write-up will be here. Clean write-up here. And here's the Simpsons cloud. So what is, and we get to assume this to be true, what is P of k? So what is P of k? Again, sounds like I'm belaboring the point, but please help me write down P of k, because you need to have these very clear in your mind as you're writing up inductive proofs in the variety of questions.
K times k plus 1 divided by 2.
Yes, that's the right-hand side, but I'm asking what's P of k? P of k, remember, that's a proposition. What you've given me, I know that you have the correct thing in mind, but I simply want people to say this as sentence.
I got you.
Yeah, so the pk is that, let me put it in quotation marks, that 1 plus 2 plus blah, blah, blah plus k is k times k plus 1 over 2, right?
So any integer times any integer plus 1
yes.
divided by 2,
yeah,
it should be equal from the 1 plus
yeah.
k integers, right?
Exactly right. That's the sentence. That is true. That's the proposition. K is an arbitrary integer. So we get to assume this is true, and now we're proving the same proposition for k plus 1. That is, we want to conclude that this is true. So let's see how we can do this. Let's see how we can do this. So this is called the inductive, in this context, this is called the inductive hypothesis. The inductive hypothesis. So by this inductive hypothesis, because we get to assume that this is true, so that is, let me just, to be clear, we get to assume that that sum here, this blue sum, is going to be k times k plus 1 over 2. Plus I have this k plus 1 term. And this is true, this line is true by the inductive hypothesis. That's why it's true. Now the rest, again, where am I headed? Why did I write it? I want to prove this. I know that this much is true, but this much is the same as what I need to prove by simple algebra. Why? So let me be a little bit clear. Now by algebra, so this is by algebra. So obviously algebraic manipulations, you get to assume that you can do them, right? This one is just simply the same as what you see below, because like if I want to be like too detailed, I'll write this as this way. Okay, although some people will say you don't need that detailed step, but let's write it out. K times k plus 1 plus 2k plus 1. And this is k plus 1, k plus 2 over 2, which is the same thing as that, what we needed to prove. Does that make sense? I've concluded the inductive step.
Yeah, so if we're gonna prove that our hypothesis is the equal to what we need to prove, so it's gonna be already proved, right?
Okay, our hypothesis is the blue part.
Yes, if we're gonna make equal our hypothesis to what we need to prove, which is k plus 1 times k plus 1 plus 1 divided by 2, we make them equal to each other. So if they equal to each other, it means we already proved that. Am I correct?
Okay, so what we need to show that peak is that, just to be clear, so maybe you said something that was correct and maybe I misunderstood you, but I will try to repeat what I think you said and you tell me if this is true or not.
Okay.
We want to show that P of k plus 1 is true, assuming that P of k is true.
Yes.
So our original implication that we had, like just to go back, we want to show that the implication is true, right? Pk implies pk plus 1.
Yep.
And so we did that discussion and said that this is the same as showing that it's getting to assume that pk is true and concluding that pk plus 1 must also be true.
Yeah, that's why we assuming our hypothesis is true.
Yeah, that's we all
we make equal our hypothesis.
What do you mean for hypothesis to equal something? A hypothesis.
pk our hypothesis, right? Hypothesis.
Yeah. So hypotheses do not equal anything.
Hypothesis case.
Sorry, one more time.
So pk our inductive hypothesis case, right? That we
okay. So just to be clear, so a hypothesis is a statement.
Yeah, I know. But
okay,
we're assuming that's true.
Yeah, we're assuming that the hypothesis is true. Yes, we're assuming pk to be true. Yes.
Yeah, so if we're assuming that's true, and made k times k plus 1 divided by 2 is true too, right? That's what we accepted in our hypothesis.
Yes, we accepted this piece here. We accepted that this and this can be used interchangeably. Anywhere we see this sum, we can write down this sum instead of it.
Yes, what I am saying is, can we just make, like, to show mathematic way, can we make equal that the red square one to what we have to prove one?
This red is equal to that. It is equal to that. We get to assume that. We do not show this. We get to assume this. Does that make sense?
I will type. I guess I couldn't explain myself. What I am trying to say is, this is true or not if we're gonna type like this. Can you see?
This is not the true statement.
We cannot do this?
No, but it is not a true statement. Plug in any k, you will get that the equality does not hold.
Oh, that's what I was asking for. Can we do this or not?
No. You cannot do this. Does it make sense why you cannot do this?
Yeah, I got it right now.
Okay, so I will return actually to this point because this. Okay, so let me conclude this proof for now. So what did we do? Let's recap what we did so far. I have not concluded the proof. We're almost there. We need to say one more sentence to say that the proof is complete. So we started here. Okay, we wanted to show that this held for any n. So we want to show that this proposition holds for any n. Right? We wrote down the proposition that we need to prove, and we checked the base case. That worked out well. Then we checked the inductive step. The inductive step says that assuming that P of k is true, P of k is that equality of these two expressions that are boxed in red, that we get to assume that those two red boxed entities are equal to one another. Those are some numbers. No matter what k is, those are equal to one another. And if they are, what we need to show that the sum of the first k plus 1 integers will be equal to this. That's what we need to show. And we did indeed show this using algebra. And of course, the assumption that the inductive hypothesis is true. Okay, so we've checked these two steps. Now going back to our template of proof, here's our template. We checked this, we checked this. So we have to write down one final sentence. We'll say, therefore, by the principle of mathematical induction, Pn has to be true for any n. That's our final statement. This is our final sentence. Does that make sense? So let's do another example. Let's do another example real quick. So we'll return to this high-level discussion again, since this needs to be talked a few times. Let's do this one, because that's what I did in the other sections. Okay, so now, again, in this example that we just did, the fact that the sum of the consecutive integers is equal to n integers is equal to n times n plus 1 over 2, that proof did not provide any insight as to why this sum was equal to that expression, like zero insight. What we did is we knew the answer to begin with, and we used mathematical induction to check, to verify, to guarantee that the answer was correct. So in terms of insight, not very useful. But in terms of being sure that this indeed is the case for every n, super useful. Now, here's another example where we are speaking about the first odd integers. Okay, like 1, that's equal to 1. That's the first odd integer is 1. What are the first two odd integers? Those are 1 and 3. That's equal to 4, their sum. What are the first three odd integers? Those are 1 plus 3 plus 5. Now I have 3 odd integers. That's 9. What are the first 4 odd integers? 3 plus 5 plus 7. That's going to be 16, and so on. Do people see the pattern here? 1 plus 3 plus 5. Maybe some pattern is about to emerge here. Who knows? This is 25, and so on. Do people see what's going on here? Now I want to conjecture. You see what's happening here. Now I want to write down this conjecture in terms of n and prove that this is true for every n. So now what is it that I'm proving? I need to be very, very clear about what it is that I'm about to prove so that I can apply the principle of mathematical induction and follow the template to ensure that some claim that I'm about to make is true for every n. But first, the real math is being done here when you're making these conjectures.
I'm sorry, the last one should be 9, right? Instead of 8.
Yeah. I was gonna say that.
That should be 9, of course. 9. Okay, so the next one is going to be 3 plus 5 plus 7 plus 9 plus 11. That's going to be 36. That's 6 squared. So what's the conjecture?
The first n integers is equal to n squared.
Okay, so n squared. So what should be my last term here? It's not the first n. If you're correct,
Oh,
the first n. Not in,
N plus
n
2.
minus.
sorry.
N plus 2.
Okay. Is n plus 2?
Yeah, because if
What
n
if
is
n is even? What if n is 2 or 4? Like one of those cases. Is
But
n plus
What
2?
talking about odd, if it's even if it's gonna be even, we should add 1 to make it odd, right?
Right. So what should I? So in terms of n, what do I have here? It's certainly
Would
not n plus 2.
Would it be
Because n plus 2 can be either even or odd, depending on what n is.
Oh,
2n over 2 maybe?
2n over 2. Why 2n over 2?
That guarantees it's a negative number, I believe.
2n
Oh wait, no,
over 2
2n over
cannot-
2 doesn't. No, 2 plus 1 maybe.
I think 2n minus 1.
2n minus 1 is exactly the answer. 2n minus 1. Why? There's 2 times 2 minus 1. That's 3. Let's use blue. 2 times 3 minus 1. Now that's definitely an odd integer, no matter what n is. This is 2 times 4 minus 1. That's 7. 2 times 5 minus 1. That's 9. 2 times 6 minus 1. That's 11. Yes, it's 2 times n minus 1. Right? So now what's my proposition? What is my, now, so, okay. So here, we haven't even started proving anything. We're still figuring out what my proposition should be, what it is that I should prove to begin with. That's where the work is. Writing out the template, once you've done like 10 exercises, that becomes straightforward. So now the next question, so what is P of n? What is P of n? So what is P of n? So let's go ahead with these. So what should I write down here? What's my conjecture? Proof is going to be by induction. Let P of n be what? Okay, so tell me while I'm writing down this, what is it that I'm proving? This is what I'm proving. This was what we conjectured. Now we want to prove it. So let Pn be what? This is even, so this is the first step, is that. You can write it in quotation marks, or you can write it in like squiggly braces, whatever. But make sure you write this down, otherwise you don't have a proof by induction. It's not clear what you're proving. What base case are you checking? Not clear. Again, that's straightforward in this case. It's exactly that, so I might as well just copy that. Actually, not that. Just that. So that's that. Okay, we want to show, actually, let me do that. I want to show, just to be clear, so that you are clear when you write this, to show that P of n is true. This is what we are showing, just for all n greater than or equal 1. This is what we want to show. Okay, so this is step number 1. Again, following the template. The template is in your reading assignment on page somewhere. You'll see it. It says, here's the template, follow this template all the time. So you'll find it. So here's the PM. That was step 1. What was the next step? What's the next step?
Basis step.
Base case, right? Is that what you said? Base case. Check the base case. So what is the base case? Why is P1 true? First of all, what is P1?
1 is equal to 1 squared.
Yeah, exactly. 1 is equal to 1 squared. Checks out. Usually easy to check the base case. Just go ahead and plug in 1 here for n, and you get 1 equals 1 squared. So that's clear. Base case was easy. It's usually easy. What's the next step? Help me out. What is it called?
The inductive step.
The inductive step. What am I proving in the inductive step?
So Pn
Uh-huh.
imply P2n minus 1.
Nope.
No?
Nope.
So
To show that P. Sorry, go ahead. Go ahead.
No, ahead, Brad.
No, go ahead. Go ahead. Who was it? I don't always see you. Who is speaking? Like, because I have 2 screens and I kind of have to shuffle through. So
Well,
please
we
wait.
want to show that
Mhm.
P of n, if P of n is true, then P of n plus 1 is true.
That's right. And we use this other variable k just to separate this n. So n is a generic variable. We want to prove that some p of n is true. Like this initial proposition is true. This p is true for every n. Now here, we fix k, but k is arbitrary. There's a subtle difference. So like, just ask me that. So to show that p of k implies p of k plus 1 for any k, okay?
So
Fix an arbitrary.
that's
Yeah.
what I say.
Okay, maybe I misheard you. So what is it that
That's fine. I say Pn implies P 2n minus 1 on this example.
but why 2n minus 1? So let me write this down. So you said p of n implies p of 2n minus 1?
Because we want to prove that 1 plus 3 plus dot 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 plus 2n minus 1 equals n squared.
Right. Yes.
So based on that,
That is that entire what you just said, right? This was this.
yes.
This is called p of n. This entire equality is indexed by n. Do you see it?
Yeah.
Okay. So this is p of n itself. This entire equality is that equality. It's either true or false. We're trying to prove that it's true for no matter what n is. That's what we're trying to prove. So now, you take now. I want now in the inductive step. I want to show that p of k implies p of k plus 1. And we're saying here, pick an arbitrary k. Just pick any k. In this range here, for any n greater than or equal, just fix any k. But that k is arbitrary. And now I want to show that the implication is true. For any k, to show that the implication is true for any k, assume that p of k is true. Assume that p of k, this I get to is true. Is true. That's my inductive hypothesis. Inductive hypothesis. Just to be clear, inductive, I get to assume this. Hypothesis. I hypothesize this is true. Hypothesis. I get to assume that. Okay, so now in your mind you're thinking, now let's be clear. So so let me just make some extra space here. So base case, actually let me make all of this very small, a little bit smaller, resize. Okay, just leave us some space. Okay, so what am I saying here? Now we're going to have all these Simpsons clouds here. What is my pk plus 1? This is my Simpsons cloud. What is pk plus 1? Because pk plus 1 is true, is what we're proving. We are proving that, quotation marks, pk plus 1 is true. Assuming, this will prove the implication, pk implies pk plus 1. Assuming pk is true. pk is true. That's what we're doing. So what is pk plus 1?
1 plus 3 plus 5 plus dot 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 plus 2 times k plus 1 minus 1. But the k plus 1 should be in a parens. So 2 times
that is exactly correct. I'll write it down slightly differently, but what you said is exactly correct. You said this, 2k plus 1 minus 1, right?
Correct.
Equals, I want to show,
Equals k plus 1 squared.
k plus 1 squared. That's exactly right. Right? So let me just, to be completely clear, I want to write down the exactly what you said, but I want to include the previous term too. So can you say it one more time?
2 times the product, or k plus 1 minus 1.
Maybe you said it correctly. Is that right?
Yes. Yes.
So you want to show that this is k plus 1 squared?
No, it should be 2k minus 1 squared plus k plus 1 squared.
Hold on a second.
No, maybe not. I just confused myself.
Okay, so let's so we want to show, here's what we want to show. We get to assume that the sum of the first k odd integers, so plugging in k here, is k squared. We get to assume that. What is the next integer after 2k minus 1? The next odd integer that I add to it. This is correct. It's just this is correct what I have here.
Okay, so
this may be what you told me, but can you write it down?
Yeah, so what I'm trying to do is replace n in the original one with k plus 1,
yes,
and then add k plus 1 minus 1 to both sides of the equation. So we should have k plus 1 squared on the right, and then
do you agree that this is do you agree that this is, you're correct? It's just maybe you gave me the expression. Maybe you were correct in the beginning too. So I don't know. I now forgot what I erased, but it's going to be on the video. Do you agree that this is the sum of the first k plus 1 odd integers? Do you agree?
Yes.
And that's what we needed to do, right? K plus, and I want to show that is k plus 1 squared. Are we all on the same page? I have exactly k plus 1 odd integers here. This is the k plus first odd integer. Okay, so now we get to assume that pk is true. So now it's algebra. What is this?
K squared.
K squared by the inductive hypothesis. What is that? I'm just rewriting this piece. But this is k plus 1 squared. Is that right? By algebra.
Yeah.
By algebra. Okay. So what have I proven? I've proven the inductive hypothesis that P of k implies pk plus 1. How have I proven it? Well, I wrote down pk plus 1. And if I assumed the blue piece, which tells me that pk is true, I get to assume this, plus some algebraic manipulation, I conclude that pk plus 1 is true. Why is pk plus 1 is true? Because the sum of the first consecutive k plus 1 odd integers gives me k plus 1 squared, which is what I wanted to prove. So this is it. The inductive step is done. To conclude the proof, all I need to say is that by the principle of mathematical induction, because I've checked the base case and I've checked the implication, by the principle of mathematical induction, Pn is true for all n, and then place QED. That's what needed to be demonstrated, and that's it. That concludes the proof. We need to do one more at least. At least, well, we don't have time for let's do this one. What is my P? Let's do this. So proof is by induction. I'm not even writing this down because I'm asked to do the proof by induction. So what is n cubed? Let Pn be this proposition. Let P of n be n cubed minus n is a multiple of 3 or is divisible by 3, any way you want to put this, or say mod that n cubed minus n mod 3 is 0, whatever you want to say. But I think it's clearer, just simply write it down in words. N cubed minus n is a multiple of 3, let's say. Let's go with one of them. Multiple of 3. Okay, so for example, when n is 5, you have 5 cubed minus 5 is 125 minus 5, which is 120, which is 3 times 40. So it's a multiple of 3. So I want to prove this not just for 5, when n is 5, but for any n whatsoever. So let's, that's my Pn. So I've written down my Pn. The goal is, so we need to show Pn is true for any n. Okay, that's what we need to show. I've gone through the first step of the template. I have my template on the side. That's my cheat sheet. I consult it. I look at it every time I see a proof by induction. Okay, so then looking at my template, I see that the next step, that was not the first step, but the next step, step 2, is to check the base case. What is the base case? Please help me out. We need to do this just following the template.
P of 1 is
P of
true
1, yeah.
because 1 cubed minus 1 is divisible by 3, or is a multiple of 3.
Exactly. 1 cubed minus 1, which is 0, is a multiple of 3. Check. Done. Usually, because it's 3 times 0, 0 is a multiple of 3. Check. Done. Next step. What is the inductive step?
P of n implies P of n plus 1. So in
Exactly.
this case, yeah, n cubed minus n is equal to n plus 1 cubed minus n plus 1. Or is not equal, sorry, implies.
Yeah, we want to prove the implication. Now I'm skipping because we're short on time, but you're exactly right. We want to prove the implication. PK implies PK plus 1. Correct. 100%. But to prove that implication, assume that for any k, PK is true. Okay, so Simpson's cloud. Simpson's. PK is k cubed minus k is 3 multiple of q. That's assume. Okay, back here. For any k, assume PK is true. Then PK plus 1 must be true because of the following. The following argument. Write down that PK plus 1. So what is PK plus 1? Again, notice the first thing I do, I'm not writing down PK. Yes, I get to assume that PK is true. But in the inductive and the hypothesis, I write down start from PK plus 1. And then whatever I do with the expression for PK plus 1, I get to assume that PK is true there somewhere. So, okay, so PK plus 1. There we're talking about PK plus 1. What is PK plus 1? Simpson's cloud. PK plus 1. What does that say? I want to show that that is 3 times something. Is that correct? Let's agree on this. That this is what we need to show. Everybody's on the same page, right? Are we all on the same page? Okay, so let's write down this PK plus 1. Okay, let's use a different color so you can see better. So k plus 1 cubed minus k plus 1. I want to show that that's 3 times something. How? Well, I get to assume this, but so I can't see it. Like, it's not clear to me why this should be 3 times something. Maybe we can somehow simplify this. Okay, let's start simplifying. K cubed plus 3k squared plus 3k plus 1 minus k minus 1. That's by algebra. I haven't used the inductive hypothesis. So far, I just simplified by algebra. Okay. Is this okay? So it looks like I can cancel these ones. Okay, that's a good start. Maybe let's rewrite. Maybe we'll see something. I don't see anything. K cubed plus 3k squared plus 3k minus k plus 2k. Is this a multiple of 3? That beats me. I don't see that being a multiple of 3. How do I see that this is multiple of 3? We only have a few minutes left to figure out. Why is this multiple? What do I do? Any suggestions? I'm stuck.
I mean,
I think you can factor out a k
Okay, that's exactly the thing that goes.
And then
Did I?
you can factor foil. Well, what's it called? Like reverse foiling, where you'll result in k times k plus 1 times k plus 2.
Oh, that's actually a good idea. If you can make it, but let's any other suggestions? Good idea. Good idea. You'll have three. Is this a product of three consecutive? I don't know if that is true actually, but I think I sort of get your idea. But anyway, can you easily see that this is a product of three? I don't. It's not obvious that this is somehow a multiple of three. It's not. I have like 2k. You can argue that this is a multiple of three. Actually, you can have some pretty nice argument, maybe somewhat complicated. But how did you get to use the inductive hypothesis? Actually, when I said it was a good idea, it may be a good idea, but where did you use the inductive hypothesis there in your suggestion? If you don't use the inductive hypothesis anywhere, then this proof cannot be complete. You've got this is somewhere you have to use the inductive hypothesis here.
Right. You know, I just said it because that's why I saw. But I didn't
Okay.
use the inductive hypothesis.
I would, you know what you just, I would just write it down because you may have a good idea there. But when you actually just flash it out, you should use the
Professor.
inductive. Yes.
So when you do factor out k, you have k squared plus 3k in there, and by the inductive hypothesis, isn't that like we know that it's divisible by 3? Like,
what is divisible by 3?
So if because we have k squared plus 3k plus 2, that 3k in the middle, we know that's our inductive hypothesis.
Where is the inductive? Here's the inductive hypothesis that k cubed minus k is divisible by 3. Where is the inductive hypothesis here? If I factor out k.
I made a misunderstanding then. Never mind.
No, you should say this. It's just maybe somebody sees that you can see an inductive hypothesis somewhere there.
So
I don't. I think you're complicating with this, but maybe I'm wrong.
So
Any other suggestions?
we can factor that out again. K times k plus 1 with
Okay.
parentheses times k plus 2. No. K times
Yeah.
k plus 1. K times in parentheses k plus 1 times again parentheses k plus 2. Yeah,
Okay.
but I couldn't.
That is k squared plus 2k. Okay. So I think initially, were you suggesting this one when I said it was a good idea?
Yeah, that's what I said earlier.
That's what you said earlier, right?
Yep.
So okay. So that's a good idea because do you see why this is divisible by 3? Do people see this? So this idea didn't come up in the other sections, and I want to show you something else. It's a little simpler to see, but that's correct. Do you see why you have 3 consecutive integers here?
Yeah.
They have to be divisible by 3.
I know that, but like I don't know how to explain why that's true.
No, it's like 3. You have 3 consecutive integers.
K
7,
plus
8,
1,
and 9. You have 3 integers in a row.
Yeah.
One of those has to be a multiple of 3. Well, how are multiple of 3s distributed?
Oh, right. Okay.
Oh, I see it. Yeah.
Yeah. So, but let's leave that aside. I want to explicitly use that's a good idea. So I would just explore that further, but we don't have time. So that's an excellent idea. But all right, so here's what I want to show you. I want to explicitly use this inductive hypothesis. So what I do is k cubed minus k. Why did I do this?
Oh, yeah. You can do a minus k, and then you could do plus 3k, and it's the same thing, plus 3k
Yes,
squared.
exactly. Yeah. Then you have actually that should be so. So I know that you see it, but I want to write down. So 3k squared plus 2k is what I had, and then plus k. So now I have that piece, the purple piece, is by the inductive hypothesis, is a multiple of 3. 3 times something is a multiple of 3. Agreed? The purple piece. That's where I get to use the inductive hypothesis. Are we on the same page?
Yeah.
This red piece is 3k squared plus 3k, which is multiple of 3, is a multiple of 3. Nobody argues it. You can factor it 3 out if you want, but so you see it, it's a multiple of 3. So the sum of the red piece, which is a multiple of 3, and the purple piece, which is a multiple of 3, their sum has to be a multiple of 3. So k plus 1, which is where we started, k plus 1 cubed minus k plus 1, has got to be a multiple of 3. There's no other way. Is a multiple of 3. This is what we conclude. Okay, so this is what we conclude in the inductive step. Conclusion. And this is our conclusion because we started here. Great. We've done the basis step. We've done the inductive step. What's the last thing I say according to my template? Here's my cheat sheet. I'm looking at the template. What's the last thing that it says on the reading assignment?
P of n implies P of n plus 1.
Yeah, so all I have to say is that I've checked, therefore, by the principle of mathematical induction, because I checked the base case and I've checked the implication, you're correct, the implication, that's checked. I can conclude by the principle of mathematical induction that conclude by math induction that P of n is true for any n. That's it. For any n. That's it. That's QED. That's QED. That's what needed to be demonstrated. What needed to be shown. Okay, so we are a couple of minutes over. But anyway, any questions about this?